There you go. Hey, gonna do something a little different today. Uh, gonna have a lot of definitions and such. So thought I'd uh, thought I'd do it this way. By the way, if you know what that song was, should send me the identification of the song, and maybe I'll give you some points for it. I doubt I will, but I might. So here's what I want to do today. We're going to talk about sequences. And for my nephew who is in my office right now, this is going to be really weird because I am going to tell a story that I've already told, but since I'm having to redo the video, he gets to hear it twice. You only have to hear it once. And so the story I'm going to tell you is how I'm a genius and how I figured out calculus when I was 6 years old. So I was out in the backyard shooting baskets, and I missed the first one, or maybe I made the first one. I don't know. But all I know is that after the first two shots, I had made 1 out of 2. And then I shot again, and I was 2 out of 3. And then I shot again, I was 3 out of 4. I was 4 out of 5. I was 5 out of 6. I was 6 out of 7. I was having an amazing streak. And at some point, I started realizing that one I had missed was becoming less and less important. And that at some point, if I could continue making them forever, then it would almost be like I had never missed one. Okay. But I knew in my head that I would always have missed that one. It could never be exactly that I hadn't missed one, because I had, but it could almost be that way. And so this is an example of something called a sequence. A sequence is a list of things in a defined order. Now, our sequences are going to be numbers, and you'll see this is our first, okay? This is our second, our third, our fourth, and so on. And in fact, in this one, we can define a formula that if the top is n, the bottom one is going to be one more. So it's n plus 1. And so the question we're going to ask is, as this thing continues to increase, as the value of n continues to get larger, does this approach a certain value? All right. So that's where we're headed. And that's what I'm wanting to see. Does this thing approach a certain value? All right. Now, I really wasn't a genius, but I like to tell that story. So if we look here, we'll see the very thing I said is that the idea of a sequence is simple. It's a list of things that have a defined order. All right. In other words, there's a first item, there's a second item, a third, and so on. We usually denote a sequence with this right here, curved brackets. All right, and then why is this all of a sudden acting stupid? All my writings are clearing. Okay. Sorry about that, but for some reason it decided to start working now. So we have a list of things in a defined order. There's a first item, a second, a third, and so on. And we're going to use a sub n. So for instance, in that list I had a minute ago, or it's right down here. All right, n over n plus 1. Well, a sub 3 is going to be 3 over 4, because that is the third term in the sequence. All right. So right there we see we have this sequence. The one below it, this is -1 to a power, and n is our power. So the first one is -1 to the first power. This second one is -1 to the second, -1 to the third, -1 to the 4th is right here, and so on. And so we see that this sequence starts at -1, then it's 1, then it's -1, then it's 1, then it's -1, then it's 1. So we can have these things defined by formulas. You can also have what's called a recursively defined sequence, and that is where the nth term is determined by something that happened before it. So a common example is the Fibonacci sequence, where the first thing is 1, all right? The second term is 1, and to get the third term, you add these two, all right? So now to get the fourth term, you add the 2 before it. To get the, let's see, the fifth term, you're going to add these 2, and so on. And this is named after Fibonacci, who developed this sequence, sequence, trying to determine the growth of a population of rabbits. That's true. And it actually tends to just show up in weird places. So let's talk about putting some definition into this idea of, like I said a minute ago, I said, it's almost like I didn't miss one. So we're going to talk about limits of sequences, and we're going to stick with this example of n over n plus 1. And over here on the left, you see there's a table, and what I've done is I've looked at these values of the sequence as decimals. We start off at 0.5, then 0.66, 0.75, 0.8. We seem to have an increasing value as we go down, and in fact, we do. But there's one thing we do know: they'll never be bigger than 1, because the top is always going to be smaller than the bottom, because the top is n and the bottom is n plus 1. All right. So the bottom is always going to be bigger than the top, so it's always going to be less than 1. And in fact, if we wanted to, we can make the difference between the number 1 and the term of our sequence as small as we want to by making n large enough. Now, that is exactly the idea of a limit, that we can make the difference between the actual value and what we're calling the limit. We can make that difference as small as we want, but just by making some other condition significantly large or small. And in fact, there's a definition of the limit of a sequence, and it says that the limit of an is L if for any positive number you think of that's, any positive number, can be very small. There's another number, and it's a whole number, such that as long as our index is bigger than that number m, then the difference between the value of the sequence and the limit is smaller than that positive value. Okay, all of that technical language means that I can make the value of this sequence get as close to the limit as I want it to be. Okay. Now, this limit is finite, then we say it, converges to the limit. If the limit does not exist or it's infinite, we say it diverges. Sometimes you might say diverges to infinity, but diverges is good enough. And then a convergent series is called convergent. A divergent series, a series that diverges, is called divergent. And with these, where I'm thinking of sequences, and these limits of sequences, all of the other rules of limits that we're used to still apply. So for instance, the limit of a sum of sequences, we can look at the two sequences separately. The limit of a product is the product of the limits. The limit of a quotient is the quotient of the limits, as long as the bottom one's not 0. If you have C times a constant times a sequence, you can take that constant outside. The limit of a constant is that constant. The limit of some sequence to a power is the limit to the power. So these are all things we've talked about before with just general limits of real valued functions, and they're still true here. In fact, we can think of a sequence as a series on the a sequence as a function on the positive numbers. So let me show you what I mean by that. All right, let's clear this. So let's say I have some function, and let's say this function looks like this. All right. So now what I'm going to do is I'm going to come in and look at the integers here. So this is 1, 2, 3, 4, 5, 6. And of course that will continue. And so now I'm going to come in and I'm going to put dots on the graph above these integers. All right. So the idea is that on this red function, I'm just going to take the y values over the integers, or this. Okay. Now, if I were to continue this process, all right, so as this goes out, I were to continue making these dots, right, at points, the limit of the sequence is the limit of the purple dots is going to end up being the same as the limit of the red line, because they're going to the same place. They're following the same path. It's just instead of looking at the whole path, we're just looking at every so many steps. All right. So that's what it means when it says here, we can think of it as a sequence on a function on the positive integers. In fact, like I just said, if you have such a function and the value of the function equals the sequence for all the values of n, and then the limits are going to be the same thing. That's exactly what I just said. And in fact, the fact that we can do such a thing is going to let us do things like use L'Hopital's rule on these sequences. Now, we don't always have to use L'Hopital's rule. We can use other things. So let's look at this thing we've been talking about. Let's find the limit as n heads to infinity of n over n plus 1. So what I'm going to do is I'm going to divide on top and bottom by n. And when I do that, I'm going to get 1 over 1 plus 1 over n. And as I let n head off to infinity, this piece right there goes to 0. So my limit is going to be 1 over 1, which is 1. So in fact, exactly what we thought about, that n over n plus 1, the values are getting larger and larger and larger. They're going to continue to get larger. They can never get bigger than 1 because, like we said, the top is always smaller than the bottom. But at some point, they start to converge, which means the values start to stack up and they're converging on 1. They may never get there, but all those values are coming together there at 1. And that's where the idea of convergence comes from. All right. Now, that algebraic trick is something you've seen before. You divide top and bottom by the highest degree of n of your variable. But this next one here, natural log n over n, that's not going to work for this problem. It would be beautiful if it would, but it won't. So we're talking about the limit as n heads over to infinity of natural log n over n. Now, if you try to directly compute this by plugging in infinity, you're going to get infinity over infinity, which is an indeterminate form, and we don't know what to do with it. So what we're supposed to do is we're supposed to consider f of x equals natural log of x over x. Right? We're supposed to note that f of x equals a sub n for x equal n. In other words, if we're on the integers, the values are the same. And then find the limit as x heads to infinity of f of x. Now, that's what we're supposed to do. And that is technically what we're doing. Okay. But what I'm going to tell you is just, I'm going to do this. I'm never going to write that. But I know in my head that's what's going on. I know I'm justified in doing what I'm about to do because I could do all of this long writing and make it justified. So what I'm going to do is I'm going to just directly apply L'Hopital's rule here, which I was taught to notate with an H instead of an L. I do not know why. The derivative of the top is 1 over x. The derivative of the bottom is 1. So when I actually take this limit, I'm going to get 0 over 1, which is 0. So the limit of natural log of n over n is 0. Now, what does that mean? It means the values go to 0, but it also means that the top is increasing at a much slower rate than the bottom. Okay, the bottom is increasing at such a rate that the top can't catch up, and the limit eventually goes to 0. All right, and right here's what I did. That whole long thing where I considered the function, that's what I did there. But for practical purposes, we're just going to directly apply L'Hopital's rule. All right, examples like the next one, -1 to the nth power. -1 to the nth power looks like this right here. It's -1, 1, -1, 1, -1, 1, and it's going to continue doing that. We can't calculate this limit, but I can tell you the limit does not exist because there's not a single value, All right. I'm going to pause this recording and see if I lost everything there because Zoom did something really weird, and I'm hoping everything will still be there when I come back. So if there's a part 2, you'll know that it worked. If there's not a part 2, you will know that, well, you won't know anything, but it'll mean it didn't work.